back, and it's a corollary is. So the easiest is a corollary. A corollary is something that follows immediately from either a proposition or a theorem. It's like maybe
a particular choice kind of thing.
So it's a particular case, more or less. I mean, if you want to prove, say that n plus n plus 1 is 2n. Suppose you prove n plus n is 2n, and a corollary of that is 1 plus 1 is 2. So corollary is like a particular case, or it follows immediately with very so there's no formal definition of all these things. It's just that you say corollary if the corollary follows very quickly from the theorem or proposition or whatever. Okay, almost as a special case. For a theorem is typically so the difference between a theorem and a proposition is more difficult. Usually what happens is that propositions are basically easier theorems. So if you're in your first standard, what would be a theorem would probably be a proposition in your 10th standard, basically. What is a lemma? Lemma is an intermediate result. Just because something is a lemma doesn't mean it's easy. It's an intermediate result that is used to prove a theorem or a proposition. So that is a lemma. So there is no real, nothing very concrete set in stone. Usually, at least when I write papers, the main result of my paper is a theorem. And anything that is much easier to prove for me, but it is not used anywhere else in the paper, is usually called a proposition. And something that is used often as an intermediate step in proving a proposition or a theorem is called a lemma. And a special case of a theorem is often a corollary. This is how I view it, but different people have different things. I hope that answered the question.
Yeah. Thank you.
Yeah.
I think if there is any questions, then participants will put a question at the end.
Please. Yeah.
They have a doubt at the place of theorem and proposition mainly.
Usually, theorems are basically harder propositions, if you will. Yeah. So that's why it's the Riemann mapping theorem and not the Riemann mapping proposition, because it's presumably a hard result. That's just that. Anyway, so begin. So the last time, so we defined angle-preserving maps. Once again, what's an angle-preserving map? Simply a map such that if you take any two curves, they go to two other curves, so that the angles between these two are the same, right? So that's the definition of an angle-preserving map. We saw why to care about these things. We proved that angle-preserving maps are nothing but holomorphic, that is analytic maps with non-zero derivative. So if the derivative is non-zero and it's an analytic map, it's angle-preserving, and vice versa. Okay. We observed that if f is holomorphic and one-to-one, then f prime is not zero. So being one-to-one is good enough to guarantee that f prime is not zero. But the other way around is not true. I mean, if you take e raised to z, it is holomorphic. Its derivative is never zero, but it's not one-to-one, right? And in fact, being holomorphic and one-to-one, meaning that f prime is non-zero, is not an easy result. I mean, it's not even true in the case of real numbers, for instance, in one-variable calculus. Then we proved this rather important result called the open mapping theorem. What is the open mapping theorem? As the name suggests, if you take a non-constant holomorphic map, it takes open sets to open sets. Open mapping theorem. So it's a very suggestive name, right? And to prove this theorem, we needed the maximum modulus principle. Yeah. So the key ingredient was the maximum modulus principle. Then we saw that certain kinds of holomorphic functions for them, you can make sense of them even at a singularity. Like, these are metamorphic functions, namely functions where the singularities are poles. They are not essential singularities. So when your singularity is a pole, you can sort of define the value of the function at that singularity to be infinity. And if you have, and you can also define 1 by infinity to be 0, and you can hope to be consistent. And indeed, you can be consistent. I mean, by pretending that infinity is the north pole of a sphere called the Riemann sphere, and the relationship between the sphere and the complex plane is through the stereographic projection. That is, you take a north pole, shine light upon the sphere, trace the light ray, it hits the sphere at one point, and that point goes to the point on the equatorial plane. So every point on the equatorial plane, which is the complex plane, gets mapped onto the sphere, and vice versa, except for the north pole. The north pole doesn't get mapped anywhere. It should be thought of as infinity. Okay? And we looked at what it meant for a map to be holomorphic from the Riemann sphere to itself. It's simply a metamorphic function on the complex plane such that f of 1 by z is also metamorphic. Okay? So any questions from the last time before we move on?
Sir,
Yeah?
some authors takes the complex plane at the south pole as tangent plane, and some authors take as equatorial plane. Which is more appropriate for stereographic projection?
I prefer the equatorial plane, you know. Just depends on your taste. Yeah, I prefer the equatorial plane. This formula is simpler.
Okay.
Yeah.
Okay.
All right. Any other
Sir.
questions? Yeah.
Sir, is there any relation with group of rigid motion? Because that also preserves angle.
But that preserves distances also, and that's the crucial difference. These things don't preserve distances; they only preserve angles.
Yes, sir. Sir,
So there's no
but
real
its
relation.
Jacobian is like orthogonal matrix, no, sir? Jacobian.
Yeah, but all I'm saying is very simple. The rigid motions preserve distances as well as angles. Conformal maps preserve only angles. So there's no real. I mean, rigid motions are special cases of conformal maps, but not the other way around. That's the thing.
Okay. Sir.
Any other questions? All right. If there are no other questions, let's move on. So conformal maps in the Laplace equation. So suppose we consider the Laplacian of phi. Suppose phi is a C2 function on an open set V, a real valued C2 function, not complex valued, real valued. And suppose we consider the Laplacian of phi, which is d square phi by dx square, which we commonly write as phi xx, plus d square phi by dy square, which is phi yy, and that's 0. This is called the Laplace equation. Functions satisfying these are called harmonic functions. The name harmonic comes from music, but that's a longer story. With phi equals c on the boundary, right? So v is a set like this, and over here phi is given to be c. Okay. So suppose z equals u plus iv is f of w. W is x capital X plus I capital Y. Suppose this is a conformal map. All right. So in other words, let me draw a picture. This is u, this is v, this is f, this is phi to real numbers, and phi satisfies the Laplace equation on the set u, on the set v, and f is a map from u to v. Okay, the coordinates here, if you will, are capital X and capital Y. Here they are u comma v. Okay, right here it is w, and here it is z. Right. Suppose it's a conformal map. What's a conformal map? Holomorphic 1-to-1. Right. and onto, okay? Such that it takes the boundary to the boundary, okay? So it's not only a conformal map on U, it extends continuously to the boundary, okay? And it takes the boundary to the boundary. The fact that it takes the boundary to the boundary follows from the continuous extension in a sense, but let's make it an assumption for simplicity. Okay? So it takes the boundary to the boundary. Now, what we will do is the following. We have a new function from U to R. We are basically, this is supposed to be like change of variables in some sense. You're changing variables, right? So you get a new function, which is phi of f of capital X, comma, capital Y. This is a new function. The old function satisfies this equation. What happens to the new function? Okay? When you change your variables, what happens? That's what we want to check. Okay? The claim is, to kill the suspense, the claim is that it will satisfy this equation again. Okay? But to prove such a claim, you need to calculate lots of derivatives, right? So it's a painful calculation, but we shall do it nonetheless. Okay, so this is phi composed with f, and d square phi composed with f with respect d square by d capital X square of phi composed with f plus d square capital Y square of phi composed with y. So this is, let's take one derivative at a time, d by dx of d by dx of this. Yeah. Now what is d by d capital X of this? By the chain rule in multivariable calculus, well, let's just recall. Sorry, I'll charge my stylus the next time, so I don't have to write like a Neanderthal with my finger. But, so what is this? This is d by dx, very simply, it is basically phi of u comma v, and u and v are both functions of x and y, so it's d phi du dx plus d phi d maybe instead of u and v I should have written small x and small y. I'm very sorry. Maybe I'll write this as small x and small y. So it's d phi d small x by d capital X. Sorry, I understand my notation is all screwed up, but it's d phi d small u capital X, d phi d v capital X with respect to capital X, likewise for capital Y. Okay? So now what we can do is ux equals vy, uy is minus vx. Why? Because f is a holomorphic map. So what you can do is that you can convert, you can, let's see, you can say that, what did we say? You can write this uy is minus vx and ux is vy, right? So I'll write that here and I'll take a derivative again. Now you'll get something very complicated. First of all, you have to take the derivative of this plus this with respect to x and this with respect to y, this with respect to y. How do you do this? You use this, do this using the product rule, and again to do this you have to use the chain rule again to do each of these. So this is uxx if you differentiate this. If you want to differentiate this, again you have to use the chain rule like this. So you'll get a complicated expression. Okay? By the way, I strongly urge you to do these calculations yourself. Just seeing the expression is not good enough. Only then will you, and even with your students, I would urge you to bring them up to the board and do these calculations so that they become comfortable. Yeah. So when you differentiate, you get this monstrosity of an expression, but happily enough, certain things will cancel out. which can be simplified using the Cauchy-Riemann equations to the following. So if you use the Cauchy-Riemann equations, I'll just give you an example. Ux is Vy. So let us see. Ux is Vy, right? Phi xy is the same as phi yx because phi is C2, so these two will cancel out. Likewise, certain other cancellations occur, and happily enough, you get a very pleasant expression. The Laplacian in the new coordinates equals the Laplacian in the old coordinates times this function. Very pleasant, yeah? So, since we know that the Laplacian in the old coordinates is 0, so is the Laplacian of this function. So why should you care about this fact? Moreover, the value at the boundary is preserved. So meaning that if we can solve the Laplace equation on an easy domain like the unit disk, centered at the origin, yeah, then we can find a conformal map to a more complicated domain. In fact, the other way around. Or maybe like this. So suppose you have a complicated domain. Suppose this is a simpler domain, right? And you want to solve the Laplace equation here. Suppose you find a map from the unit disk to this, or rather, maybe the other way around. Sorry. Maybe you, whoops. If you want to find a harmonic function here, if with a certain boundary condition, and if you use the same boundary condition, you find one here, not the same boundary condition. Basically, this goes to this on the boundary. So at this point, whatever the value is at this the same value over here. You can solve this. This is easy, quote unquote. And if you find this map, then you can solve it here. Okay, so the difficulty would then boil down to finding out this map. Okay, so we can solve it on the latter. Okay, so this is a beautiful way of solving a partial differential equation on a complicated region using a solution on a simpler region if we can find this conformal map. How do you do that? That's not easy, by the way, but at least we know something here. A useful thing to keep in mind is that if f from u to v is conformal and g from v to w is conformal, then f composed with g from u to w is conformal. Why is this true? Why is this fact true?
Sir, 1 is and just differentiating will give non-u.
Sorry, 1 it's of course if f is 1 to 1, g is 1 to 1, f composed with g is 1 to 1, that's good. What about the holomorphic part?
So holomorphic composition up to holomorphic function is again a holomorphic function.
Right. It's a holomorphic function. I hope you've seen it. If you haven't, the easiest way to prove it is the composition of C1 functions is C1, and you can use the chain rule to show that the composition satisfies the Cauchy-Riemann equations. Okay, it's easiest in the sense that it does not require much thought, but it requires a lot of calculation. There are some proofs which are easy in the sense that they don't require a lot of calculation, but they require a lot of intelligence to think of the proof. They are not easy, to be honest. Yeah, right. But anyway, so this is the case. So my point is, sometimes if you have a complicated domain, you can make it slightly less complicated, and then a little less complicated, and finally become the unit disk, for example. You can do it in stages. That's the point of this observation. Okay. Okay, so this is the chain rule. F composed with G is holomorphic, and it's 1 to 1. All right. So let's look at examples of conformal maps. Yeah. F of z equals z squared. It's not 1 to 1, right? It's holomorphic. It's not 1 to 1. Well, it is if you take the open semi-disk to this. So in other words, if you take this to this, this is holomorphic and it is 1-to-1. Why is it 1-to-1? If you give me anything here, right? What is this unique square root here? You just halve the angle, so you'll get an angle between 0 and pi, and just take the square root of the distance. So you'll get a unique complex number here. Okay? So everything is unique. I mean, we are throwing this part out. Okay? So this is it takes the open semi-disk to the unit disk minus the non-negative, the positive real axis. We are throwing that out. Okay, so this is a conformal map. Okay. So when you say something is 1-to-1 or not, that depends on your domain, as you very well know from inverse trigonometry. I mean, in that case, the range, but in general, okay, the domain and the range affect whether something is 1-to-1 or not. Yeah. So suppose we want to take the unit. So this is how we can take this open semi-disk centered at 0 to this. What if we want to do something slightly different? Oops, sorry. What if we want to take the open unit semi-disk centered not at 0, but at 1 plus square root of minus 1, right, to the same place. Suppose I want to do, maybe not this, suppose I have something here, not at the origin, and I want to do the same thing. What I can do is I can do it in stages. I can take this to this first and then this to this. When we first translate this way, so that 1 plus square root of I minus 1 goes to the origin. First you do this, and then you do this. And then to make the center of the unit semi-disk the origin, then apply z squared, meaning the final map is the composition of these two, which is this. Okay? So it helps to break down what you want into tiny little pieces, and each piece you can handle. Yeah? If we further want the image to be centered at some other point, as in instead of wanting this, suppose we want it to be centered at, let's say, minus 1. Then you do the same thing and you translate the image. Okay, we translate again. So the answer would have been this thing minus 1. Okay? So this is a very straightforward and silly kind of an observation, but it's very useful. Okay? So you can, by doing these translations, you can assume that your favorite point in the domain is the origin, your favorite point in the range is the origin also. Okay? One can use square root of z with the right branch to do the inverse operations, in the sense that if I ask you the opposite question, make this into this, you can just take the inverse of this function, square root of z, except you have to use the correct branch of the square root. So I hope you've seen this word, branch. Has this been mentioned by my colleagues?
Yeah, it was discussed.
Okay, wonderful. All right. Here's another example. F of z equals e raised to z. It is, of course, not 1-to-1 when you look at the entire complex plane. However, it takes, how does e raised to z fail to be 1-to-1? E raised to z1 equals e raised to z2, if and only if e raised to z1 minus z2 is 1. When is e raised to anything 1? When this imaginary part of z is a multiple of 2 pi I, an integer multiple of 2 pi I, right? So in particular, if you want to make it 1-to-1, you should take a narrow strip in the y direction, right? Something like this. So if this is pi, like so this is 0 and this is pi, for example, then it is 1-to-1 here. The exponential map is 1-to-1 here, because you can get a unique angle in this domain. Okay, and it takes it where? To the upper half space. How do I know that? So it's not very difficult. E raised to z is e raised to x into e raised to I y. So since there is no restriction on x, that means the radius of the complex number, the distance from the origin, can be any positive number, right? However, there's a restriction on y. That means the angle should be only between 0 and pi. That means it has to be the upper half space. Okay? So it's very easy to see that e raised to z takes this particular open strip in a 1-to-1 holomorphic manner to the upper half space. Yeah? What if I want to do the following? What if I want to instead take this, not to the upper half space, but if I want to take it to, let's say, the left half? Okay, if I want to do this instead of this, what should I do? Well, you can take this to this first, and there's a way to go from here to here. How? You can simply rotate this thing by 90 degrees. What operation accomplishes rotation of complex numbers by 90 degrees? Simply multiplying by the complex number I. So if I take I times e raised to z, it takes this particular strip to the left half space. Yeah? And likewise, so a combination of these rotations and scalings and translations can already do lots of things, right? On the other hand, if I rotate the domain, then instead of this, it takes a rotated strip to the upper half space. So what strip? Does it take this strip to the upper half space, or does it take the left strip? Does it take the left one? I mean, in the sense, does it take this to this, or does it take the right one to this? In other words, my question is, does it take 0 less than x less than pi to the upper half space, or does it take minus pi to the upper half space? Which of these?
Lift off.
Actually, not quite. It takes this one. Why? Because if you take the right half, when you multiply by I, it gets rotated by 90 degrees. So this becomes the x-axis, and this becomes this. If I were to just write formulae, sorry. You're right. It's the other way around. Let's actually just write formulae. If I take, instead of this, if I take e raised to I times x plus iy, this is e raised to ix minus y. Okay, so let us see. So what do we want? We want, so if x is between 0 and pi, then this is in the upper half space, because this is e raised to I theta, right? When theta lies between 0 and pi, you're in good shape. So yeah, so in other words, it takes this right half to the upper half space. Okay, so not the left half, takes the right half. Indeed, you can very well imagine if I take this strip and if I multiply by I am going to rotate this by 90 degrees, so it becomes like this. Okay, rotate it by anti-clockwise. Okay, right. So in other words, now we have one more thing at our disposal. We can rotate the image, we can rotate the range, we can translate the image, we can translate the domain, and we can translate the range. Okay. Let's do one more example, and this one is also an important example. F of z equals 1 by z takes the open unit disk minus the origin. This is sometimes called the punctured open unit disk because you put a hole in the unit disk, a puncture, to the exterior of it. What does that mean? That means if I have anything here, if I apply 1 by z, it goes here, outside the unit disk, right? Because why? Because if I take 1 by z and take the magnitude, it's 1 by mod z. So if mod z is less than 1, this is larger than 1, okay? And this is 1 to 1. Likewise, it takes the exterior to the interior minus the origin. So if it takes anything here to this. So sometimes this is called inversion. Okay. All right. So as a homework exercise, you will see that f of z equals half of z plus 1 by z takes the punctured open unit disk, this thing, to everything except, very, very interestingly, except the interval between -1 and 1 on the x-axis. Except for this thing, everything else conformally. Very curious, very interesting map. Takes the punctured unit disk to C minus -1, 1 conformally. Okay. So this might raise a question: how the hell do you know the image, right? It sounds like, I mean, these are very easy. This example, this one, etc. You can very quickly see what the image should be. This one it looks very formidable, and indeed it's not trivial. In your homework, I gave it as a guided exercise, which is there's a small elegant trick. But in general, how does one find out the image? So note that, so maybe I'll tell you, maybe I should have written the trick earlier, but the idea is, if I give you an arbitrary conformal map, what you can try to do is to see where it takes the, so from the unit disk to somewhere, you can look at where it takes the radial lines and where it takes these circles. Okay, it'll take them also to things like this only. Like what I mean is, suppose I take the unit disk, and if I want to find out the image of a conformal map, I just need to look at these radial lines. They'll look like this, whatever. These radial lines and these circles, they'll probably look like this, right? So you can get to know what the shape of the image looks like if you know these things, the shapes of these things. In a sense, you can get to know what the image looks like, okay, and vice versa. Okay. All right. Or sometimes if you want to look at all of C, you can just look at, I mean, not maybe these or maybe these. Depends, right? It's an art more than a science, but something like this. Okay. So if we know this, notice that we can do something very interesting. If you take cosine z, what is cosine z? It is half of e raised to iz plus e raised to minus iz, right? By Euler's formula, by writing the Taylor expansion, for example, right? Now, this function, suppose you want to know what the range of the cosine z function looks like, okay? This is a composition of a rotation with the previous function. In other words, I can take z to iz and then apply this, right? So if I take the punctured unit disk, that goes to the punctured unit disk. And I know where this goes. This goes to C except for -1, 1. Except for this, everything else, right? So this takes this to this. So cosine z takes this piece to this, right? So as I said, sketching what happens to the coordinate grid under these maps is instructive. That is either these radial lines and these circles or the usual Cartesian coordinates. The polar coordinates or Cartesian coordinates, look at the coordinate grid, whichever is appropriate, and see what happens under these conformal maps. Then you can get a rough idea of what the image looks like. Okay? And this stuff is fun. I mean, you can give problems of this sort to your students and see. Okay? All right. So we will focus our attention in this lecture, possibly a part of the next lecture too. I don't remember, but these lectures, we will focus our attention to some very specific kinds of examples of conformal maps. Okay, these conformal maps are called Mobius maps. These Mobius maps, this Mobius is the same Mobius of the Mobius strip. That is, if you take a piece of paper, a rectangular piece of paper, and what you do is you twist this end and identify with this, right? So what you do is, it's commonly written like this: you take this point and identify with this, you take this point, identify with this, you twist it and then glue it to this edge. You'll get a fairly strange looking piece of paper that has no inside or outside. It's a very interesting object. It's the same mathematician who came up with these Mobius maps. So recall translations, that is z goes to z plus a, rotations plus scaling, that is z goes to 2z scales. Okay, it's like changing the units, right? And z goes to something like iz rotates. I mean, in fact, z goes, say, I pi by 4, z will rotate by pi by 4. And if you take the composition of these two, 2I pi by 4 z goes to 2 e raised to I pi by 4 z will rotate z by 45 degrees and then scale it by 2 units, right? Inversions means that you basically invert, take this to this and this to this, okay? So these, recall these conformal maps. These are conformal maps of the Riemann sphere. What the hell does a conformal map of the Riemann sphere even mean? What do you think it means? So we know what a conformal map from a domain in complex plane to another domain in the complex plane, what that means. But what does a conformal map of the Riemann sphere mean? What's the meaning of that?
Sir, extended complex plane.
Okay, that is the Riemann sphere, sure. But what is the definition of a conformal map of the Riemann sphere? That's my question. All right. So what is the definition of a holomorphic map from the Riemann sphere to itself? We did this in the last lecture. What do I mean by a holomorphic map from the Riemann sphere or the extended complex plane, whatever you want to call it, to itself?
Is a metamorphic map from C to C, and f of 1 by z is also metamorphic.
Very good, right? So basically, a map of the extended complex plane or Riemann sphere or whatever to itself is simply a metamorphic function such that f of 1 by z is also metamorphic. In what way is it a map from the extended complex plane to itself? What is a metamorphic function? The only thing, basically it's more or less like a holomorphic function, except it has singularities which are poles. So take all the poles to infinity and take infinity to wherever f of 1 by z takes 0 to. F of 1 by z is also metamorphic, no? So it takes 0 somewhere, meaning suppose g of z is f of 1 by z. Either 0 is a pole, in which case take it to infinity. Otherwise 0 goes somewhere, so take it. So take infinity there. Okay? That is a holomorphic map from the Riemann sphere to itself. A conformal map is simply a one-to-one holomorphic map from the Riemann sphere to itself. The inverse of this is also going to be a one-to-one holomorphic map from the Riemann sphere to itself. That is what a conformal map of the Riemann sphere is. In other words, in plain English, you can just extend these to infinity also, and to places where this becomes infinity. Okay? Basically, we are including infinity. In other words, infinity under a translation goes to infinity. Under a rotation, it goes to infinity. By the way, A is non-zero here. And under an inversion, infinity goes to 0, and 0 is a pole, it goes to infinity. Okay? So that's what happens to the Riemann sphere. By the way, it's a very fascinating exercise to do the following. Look at the stereographic projection, right? When you do a translation, what really happens to the sphere? That is, if you take z to z plus a, and you map this to the sphere using the stereographic projection, and you map this to the sphere, what is really happening to the sphere? What do you think happens to the sphere? If you take a translation of the complex plane and look at what happens to the sphere under the stereographic projection, what do you think happens? Oh, sorry. What I mean is, I'll just ask the question again. Suppose I take z goes to z plus 1. Okay? This is a map from C to C, right? So you can think of it as a map from the Riemann sphere to itself, right? It takes infinity to infinity. It takes the north pole to itself. It takes this, okay? So where do you think, so the south pole corresponds to z equals 0. So the south pole does not go to itself, it goes somewhere else. It goes to this point. Anyway, think about what this is doing to the Riemann sphere. Something that is a little easier is what happens to these things. Rotations plus.
Sir, origin is shifted from one to another. 0 to another point.
That is true. But it's instructive to look at what is exactly happening on the sphere itself. But anyway, maybe if I look at something like this is a little easier. Suppose I take z goes to iz. That's a little easier. Then what happens is the sphere gets rotated. Even if you take an inversion, it corresponds to some sort of a rotation of the sphere, roughly. It's instructive to see what these things do to the sphere, actually. Okay. Anyway. So what does this statement mean? It means whenever we want to deal with infinity, we use an inversion and study w equals 0. So you have to be careful with things like this. This is the only thing that can go wrong, and these are not defined. You have to be careful. Okay? When you look at examples, it will be very clear as to what I mean. So these maps, translations, rotations plus scaling, and inversions, they're all special cases of this map. Why are they all special cases of this map? If I put C to be 0, what will I get? I'll get AZ plus B over D. So suppose I now put D to be 1, and if I put A to be 1, then I'll get Z plus B, which is a translation. If I put B to be 0 and D to be 1, I'll get AZ, which is this. If instead I take A to be 0, B to be 1, D to be 0, and C to be 1, I'll get an inversion. So they're all special cases of this map. Okay. However, there is a big problem with this map. The problem is, what if you ever encounter 0 by 0? That's a very dangerous situation, right? You don't ever want to encounter that situation, right? So when can that happen? If AZ plus B is 0 and CZ plus D is 0, then what happens? Then AZ equals minus B, CZ equals minus D. So ADZ equals minus BCZ, right? ADZ is basically minus, so if I multiply by BCZ, it will become B, sorry, this, right? So since this is the case, when is this going to be true? This is going to be true either when Z is 0, in which case B is 0 and D is 0, or if Z is non-zero, AD is BC. But even in this case, AD is BC, right? So in that case, if AD is BC, f of Z is a constant for all Z, and we never count constants as conformal maps. Why? Because they are not one-to-one. So we want to ignore this possibility. So we do not want constant maps, and hence always impose AD minus BC to be non-zero. Okay? Now, this is a map from C to C. Does this give you a map of the Riemann sphere to itself? Well, for that, we have to know whether this is a metamorphic map. Of course, it's a metamorphic map, because the only thing that can go wrong is when the denominator is 0, and that's a pole. So when the denominator is 0, it goes to infinity. And f of 1 by z is also a metamorphic map, because it is a plus bz by c plus dz. It's exactly of the same form. So that's also a metamorphic map. Therefore, this can be thought of as a map from the Riemann sphere to itself. And where does it take this pole to? It takes it to infinity. That is when cz plus d is 0, or in other words, z is minus d by c. You're dividing a non-zero number by 0, and we declared it to be infinity. Likewise, when f of infinity is a by c. Why is this true? This is reasonable. Why is this true? How can I figure this out?
Divide by z.
Okay.
Numerator and denominator.
Okay, you divide the numerator and denominator by z, then you take this to be infinity, and we declared this by infinity to be 0, right? That's one way. Another way is to say that you take f of 1 by z. This is a more systematic way, the way I'm going to tell you right now. Take f of 1 by z, it is a plus bz by c plus dz, and substitute z equals 0 here. So this is 0, this is 0, it's a by c. Okay, that is the correct definition of f of infinity. You take f of 1 by z and substitute z equals 0. Okay? Wonderful. So this can be thought of as a map of the extended complex plane to itself. It takes this point to infinity, and it takes infinity to this point. Okay? Now, clearly, compositions of these maps are also conformal maps of the sphere if AD minus BC is non-zero. This is not so clear, This will be a part of your homework. That is, if I take two such maps, and if I compose them, that is, if I apply them one after the other, they will continue to be of the same type. Okay? Okay, maybe this is not a part of your homework. I'm actually doing it here. So, so first of all, compositions of these maps. I think I was trying to say something else here. This part, please, what I'm trying to say here, I mean, ignore the word indeed here. These two are two separate sentences. What I'm trying to say here is that these maps are actually one-to-one. Forget about this. Maybe what I'm saying is clearly these maps are conformal maps of the sphere. I should have written this more clearly. I was mixing up two things. What I meant is not compositions. These maps are conformal maps of the sphere. Not also, just conformal maps. Why are they conformal maps? What is a conformal map? What is a conformal map of the Riemann sphere? It's a metamorphic map from C to C such that f of 1 by z is metamorphic. That is true. And it is one-to-one. Why is it one-to-one? Suppose these two are equal. Okay? Then that is true if and only if this happens. And therefore, these two are equal if and only if AD minus BC is non-zero, and that is what happens here. That is the assumption made here. So my point is these maps are conformal maps of the Riemann sphere. Sorry, any questions?
No, actually, that sentence is also correct because that bilinear transformation can be written as a composition of those elementary transformations. Maybe indeed, with that it may be correct.
Maybe that is what I meant, but
Yes,
I'll say that later also again. But thanks, yeah.
So there is no mistake. That is correct also.
Right. So, so yeah, the comment made just now, I'll just clarify that in a moment. Let me just finish this point. So these maps, AZ plus B by CZ plus D, where AD minus BC is non-zero, they are called Mobius maps, or sometimes they're called fractional linear transformations. Why are they called fractional linear transformations? Well, technically, this is a linear map. This is not a linear map. It is, the correct name for this is an affine map. But anyway, even if you want to call this a linear map, this is a ratio of two such maps. That's why they're called fractional linear transformations or Mobius maps. Okay, AZ plus B by CZ plus D, provided AD minus BC is non-zero. This is crucial. Okay, so yeah, the comment that was made just now, that will come up and probably in this slide anyway. So I'll just move on to this. So it turns out that every conformal map from the Riemann sphere to itself is a Mobius map. In other words, these are the only conformal maps from the Riemann sphere to itself. There are no more. This is not trivial to prove. It requires some more mathematical machinery, and we will prove this statement, but it requires a lot more work. Okay? Before we discuss the proof, we need to look at some properties of Mobius maps. Okay? So firstly, and this is related to the somewhat unclear statement in the previous slide. So this will be a homework. A composition of two Mobius maps is also a Mobius map. What does that mean? If I take a map of the type AZ plus B by CZ plus D, where AD minus BC is non-zero, and another map of that type, like let's say alpha Z plus beta by gamma Z plus delta, where alpha delta minus gamma beta is non-zero. If I compose them, that is, if I apply them one after the other, then the resulting map is also going to be of this type. What do I mean by this type? I mean it's going to look like this, where this condition is met. Okay. It's very easy to see that it will be of this type, as in it will certainly be of this type. The fact that this condition is met follows from this point, that the composition of two one-to-one maps is one-to-one, and this sort of a map is one-to-one always because of this condition. Okay. Right. Sorry about this. Right. So this is a part of the homework. Every Mobius map is invertible. It's a one-to-one map from the Riemann sphere to itself. It's not shocking it's invertible. The composition is associative. Of course, composition of functions is associative, so sure. The identity map is a Mobius map. Of course, Z goes to Z is a Mobius map. So the Mobius maps form a group. I hope everyone here knows what a group is, right? So the collection of all Mobius maps forms a group. Now, of course, the real question is, why the hell should you care? I mean, okay, it forms a group, so what can you do with it? I mean, it's just convenient language as far as elementary complex analysis is concerned. It has no deeper meaning. In more advanced mathematics, it does help with other things and so on. But as of elementary mathematics, it's just convenient language. It's an infinite group. Maybe if your students ever ask you to give them a nice example of an infinite group, I'm sure you can give lots of examples like Z with addition, but this is also a very nice example. It's called a Mobius group, and it's denoted like this because of this theorem. Every conformal map of the Riemann sphere to itself, that is, every automorphism of the Riemann sphere is a Mobius transformation, and therefore this is sometimes denoted like this. Okay. All right. Moreover, Mobius maps, this is the comment that was just made, are compositions of translations, rotations plus scalings, and inversions. Meaning that every map of this sort can be obtained using these three kinds of maps applied one after the other in the correct order. Okay? You take these maps and apply them one after the other a finite number of times, a correct collection of these maps, you'll get every map of this sort. It's a very, very nice property of Mobius maps, right? In group theoretic terms, this group is generated by these kinds of elements. Okay. This is very, very, very helpful, as we will see in proofs later on. Every Mobius transformation can be obtained using this, this and these three kinds. Okay. This will be a part of your homework, I think. Yeah, I didn't prove it here, so there's also a part of your homework. Okay. All right. So, any questions so far? Right. Let's move on. So, Mobius maps fixed point.
Excuse me,
yeah.
sir.
Yes.
Yeah. So, set of all Mobius transformations forms a group.
Yeah.
Okay. Then we can say that the elements of automorphism from C cap is also Mobius transformation.
No, we can't. No, we can't. That is a theorem. That's a difficult theorem that we'll prove later on. I'm only saying that the fact that the Mobius transformations are all automorphisms is a theorem, but because of that, the notation is this. The reason the Mobius group is denoted like this is because of this theorem. Maybe I'll just remove this if this is confusing. It's not relevant. Okay.
Okay.
All right. Okay. So any other questions? All right, let's move on. So fixed points. A Mobius map can have fixed points, namely points Z that are not moved. In other words, f of Z equals Z. That is AZ plus B divided by CZ plus D is Z. let's see what kind of fixed points it can have. So the point is that notice that Mobius maps are defined on the extended complex plane, right? So you have to treat the cases where z is infinity and z is minus d over c separately, okay? So suppose z is infinity, then this thing is defined to be a by c. Suppose infinity is a fixed point, that means a by c is infinity, that means c is non-zero, I mean c is 0 and a is not 0, okay? Of course, AD is not equal to BC, so if c is 0, then this is 0, so a and d are not 0, right? So if infinity is a fixed point, that means c is 0, which means in that case, the map is precisely of this type. It's a composition of a scaling plus a translation plus rotation. In other words, infinity is a fixed point if and only if the Mobius map is of this type, okay? So in this case, there is exactly one fixed point, and that is infinity. Right. I mean, not exactly one fixed point. It is, sorry, it has a fixed point, which is infinity. It can have other fixed points too, which we'll just find out in a moment. So suppose in this case, let's try to find out all the other fixed points. It's actually az plus b over d. I forgot the d. But that is a by d z plus b by d. If I want, I can define this as some a prime and this as b prime. And it'll look like this, okay? But anyway, so if az plus b by d equals z, and z is not infinity, then z is equal to b by d minus a, yeah? So if a is equal to d, then again z is going to be infinity, and b is non-zero, then z is going to be infinity. So in other words, the map z goes to z has infinitely many fixed points, of course, many fixed points. The map z goes to z plus b has exactly one fixed point, namely infinity. The map z goes to az plus b, where a is not equal to 1 and b is not equal to 0, that has two fixed points, namely infinity and this. In fact, even if b is 0, that's not a problem. It has two fixed points, this and this, okay? Right. So, all right. So that's that. The other situation is, sorry. Okay. So that is this particular thing. So suppose c is not 0. If c is not 0, then the map is of the type az plus b by cz plus d. Infinity is not a fixed point. Okay, if infinity is a fixed point, only when c is 0. So here infinity is not a fixed point. Okay. Now, if c is non-zero and the denominator is 0, then this becomes infinity, which is not possible because this is not equal to infinity, because c is not equal to 0. All right. So if c is non-zero, the only fixed points it can have will satisfy this equation. You multiply this with this and you'll get a quadratic equation. Therefore, you get this quadratic equation, cz square plus d minus az minus b equals 0. Okay? Therefore, there are at most two fixed points in this case. Okay, because there are two roots of this quadratic equation. There could be only one root also. When can there be only one root? When the discriminant is equal to 0. In this case, there's exactly one root. Otherwise, there are two roots. So the roots are given by the familiar quadratic formula. So if the discriminant is b square minus, so it's minus 4bc. I'm sorry about that. So b square is, if a minus d whole square is minus 4bc, then we have coincident roots equal, both are equal to this. Okay? If not, we have two fixed points. To summarize, we have either one or two fixed points, or, sorry, infinitely many. This is for z goes to z. I forgot to write that down. I'm sorry about that. So for Mobius maps have either infinitely many fixed points or one or two fixed points. Okay. So one fixed point occurs either for pure translate, the exactly one fixed point case occurs either in this case when it's a translation that is at infinity, or in this case. Okay, there I forgot a minus here. In every other case, you have either two fixed points. I mean, z goes to z, you have infinitely many fixed points. But in every other case, you have two fixed points. Okay? While these two one fixed point cases appear different, they are actually secretly almost the same. Okay? So I'm saying that one fixed point occurs, exactly one fixed point occurs either when this happens or when this happens, right? And these two appear to be two different cases, but actually they're one and the same thing in disguise. Okay, one of them is wearing a mask, which you're not able to see. Indeed, suppose you take this case. You have exactly one fixed point when the discriminant is non-zero. Then what you can do is the following interesting thing. You can send it to infinity using this particular Mobius map. Okay? You can send any point you want to infinity using Mobius maps. How? Just take 1 by z minus gamma. When z equals gamma, you get 1 by 0. This is infinity. Right? So in other words, in this case, gamma goes to infinity. This is a very nice little operation. Okay, what this does is that it takes infinity to infinity. Why? Infinity is taken by G inverse to gamma. F takes this F takes gamma to gamma. It's a fixed point. G takes gamma to infinity. So this is a Mobius map. Why is it a Mobius map? Because Mobius maps, I told you that in your homework you show that it's a group. So this sort of a thing is a Mobius map. It takes infinity to infinity, and crucially, f of z equals z if and only if g of f of g inverse z equals z. That is, if and only if g of f of w that means that this has the same number of fixed points as f. Okay. In other words, this case and this case are secretly one and the same. You can make this case into this case using this nice little transformation. If you're familiar with group theory, such an operation is called conjugation. In group theory, a conjugate of a group element is like this. If you conjugate f by this g, then these two are the same. They're conjugates of each other. Okay? So thus h of infinity is infinity, and h has exactly one fixed point, which means h is a pure translation. Okay, so pure translations are conjugates of the case where the discriminant is 0. Okay. Any questions so far about fixed points before we move on to another property?
I
All
think
right.
there are no questions.
Okay. So, so the next order of business is the number of parameters. So the question is, how many free parameters determine a Mobius map uniquely? Okay. So a Mobius map, there are lots of Mobius maps, right? I mean, if you choose values of A, B, C, and D so that AD minus BC is non-zero, you get a Mobius map. Then, and for every such choice, you get a Mobius map. So how many free parameters determine a Mobius map uniquely? How many do you think?
3.
Why 3? There are 4 numbers, no? A, B, C, D.
But by choosing 3, we can get the another one fixed, right?
Not quite,
No. AB minus BC is non-zero.
Non-zero, that's all.
So divide one constant.
Sorry?
We have 4 constant A, B, C, D. We can divide one constant.
Right, that's exactly what happens. So naively, it seems that we need 4 complex numbers, A, B, C, and D. However, if you rescale these numbers by a complex number, a non-zero complex number, it does not change the map. That is, this is the same as this. So by rescaling, you can assume that if one of these is non-zero, surely one of these is non-zero, you can assume that that is equal to 1. That's equivalent to dividing by that constant. So secretly, you only have 3 free parameters, not 4. Okay. Thus, we only have 3 free complex parameters. So we expect that there exists a unique Mobius map mapping 3 given distinct points in the Riemann sphere to 3 other given distinct points. In other words, you have 3 free parameters at your disposal. So if you give me 3 complex points, you should be able to map them to 3 other complex points by tweaking these 3 free parameters. That's what we expect. And we expect that there's only a unique map that does the job. Yeah? Because you would have exhausted all your degrees of freedom, roughly speaking. Okay? So indeed, this expectation is correct. Okay? We shall prove that Z1, Z2, and Z3 can be mapped uniquely to 0, 1, and infinity using a Mobius transformation. Okay? By the way, since some of you asked me the difference between, say, a proposition and a corollary, this is a proposition. It's not quite a theorem because it's not such a hard result to prove. It's a proposition. It can also be a lemma because it's useful in other places. But as a corollary of this proposition, this expectation follows. This is a corollary. Why? Because it follows very easily from the proposition. How? Because if you can map any 3 things to 0, 1, and infinity, and if you want to map these 3 to these 3, what should you do? You should simply map these 3 to this, these 3 to this, and take the inverse. So you go from here to here and then here to here. By composition, we can uniquely map Z1, Z2, Z3 to W1, W2, W3. Why is it unique? Suppose you have 2 such maps, right? Then what happens is that using the inverse, you have a map from that takes Z1, Z2, Z3 to Z1, Z2, Z3, but it is not the identity map. But that's a problem because you can take Z1, Z2, I mean, why is that a problem? Because, for example, if you take, you can first map Z1, Z2, Z3 to this, and there's only one map that takes 0, 1, infinity to 0, 1, infinity because of this statement. So this is a corollary. So the real difficulty would lie in proving this. Okay. So how do you map these 3 points? Assume that none of Z1, Z2, or Z3 is infinity. Okay. If one of them is infinity, then it's not very hard. I'll come to it in a moment. But let's assume none of them is infinity. So we want Z1 to go to 0, Z2 to go to 1, and Z3 to go to infinity. Since Z1 goes to 0, f of z is of this type. Why? Because az1 plus b is 0. So that means b is minus az1. So it's of this type. Since z3 goes to infinity, if you substitute z equals z3, you'll get this. When can something go to infinity? Precisely when the denominator is 0. So this is 0. That means d is minus cz3. In other words, this is c times z minus z3. However, a by c can be denoted as the constant a. You can just write a by c as another constant. If you want to, you can write it as a prime, but I wrote it as a. Okay. Now z2 goes to 1. Therefore, az2 minus z1 divided by z2 minus z3 equals 1. So you can solve for a as z2 minus z3 over z2 minus z1. Very trivial, right? Therefore, f of z is actually z minus z1 times z2 minus z3 divided by z2 minus z1, z minus z3. So this very easy thing, it's a proposition. That's why it's not a theorem. It's so trivial. Maybe we can call it a lemma also. It might be useful elsewhere, but not exactly. Right. So, therefore, using the corollary of this proposition, we can map any 3 points on the plane to 3 other distinct points, provided none of them, any 3 points on the plane, not on the extended plane, not on c hat, because we have not dealt with the case of infinity yet. So suppose one of them is infinity, suppose z1 is infinity, then infinity should go to 0, right? What is f of infinity? By definition, it is a by c. It is 0, that means a is 0. So f of z is of this type. It's b divided by cz plus d. Since c is non-zero, we can divide by c, and we can call this as b and this as d. Okay? Now, suppose since z1 goes to 0 and z3 goes to infinity, that means when z3 is infinity, so that means d is minus z3. And f of z2 is 1, so you can simply say that b is z2 minus z3. So we can map infinity, z2 and z3 to 0, 1, and infinity. What about if z2 is infinity? Basically, z1 goes to 0, z2 goes to 1, z3 goes to infinity, right? So first of all, so where does infinity go to? It goes to a by c, and that must go to 1. So that means a is equal to c. So that means f of z is az plus b over az plus d. So since z1, f of z1 is 0, we get this. And since f of z3 is infinity, the denominator must be 0, and we get this. So we can solve that case. So if z3 is infinity, that means infinity goes to infinity. So infinity is a fixed point precisely when c is 0. So it's of the type az plus b. Since f of z1 is 0, this is of this type. And since this is the case, we'll get this. So in other words, so we prove the complete result. Namely, we prove that this thing, if this is in the extended complex plane, then you can still map it to these things. Okay. Therefore, using this, you can prove this expectation. Okay.
Sir?
Yeah.
Sir, why we are taking 0, 1 and infinity point only? Can we take any other point, 1, 2, 3 or some other points, and then can we do these calculations?
You can, except what makes 0 and first of all, 0 and infinity are very pleasant, because if something is 0, you already know the numerator is 0. If something becomes infinity, you know the denominator becomes 0, right? So it's very quick. It's very easy to solve for A, B, and C and D for 0 and infinity. And 1 is much easier to handle than 2, right? That's why. There's no particular reason other than that. Okay. You can try doing the same things with 1, 2, and 3, but be my guest, but it's much more painful. Right, so we have roughly 10 more minutes. So let's see. Right, so any questions about this particular property? Right. So next we move on to geometric properties of Mobius maps. So the real question is, maybe someone asked me this question that in the last lecture, I think, that what about rigid motions? Rigid motions are basically these things that preserve distances in R3 or R2, for example. And what are rigid motions? Rigid motions are basically translations and rotations. Any combination of these, it gives you a rigid motion, right? So if you ask me the following question, if you take the distance, if you take Euclidean geometry, that is, you take the usual distance on the plane and ask me what quantities, maybe not like that. What I mean is the following. Suppose I ask you the following geometric question. Consider translations and rotations. And if I ask you a question of this type, what quantity does not change under translations and rotations? Okay. What quantity does not change under translations and rotations? The distance between 2 points, right? The distance between 2 points is unchanged under translations and rotations. Unfortunately, Mobius maps are not just translations and rotations. They involve scaling, they involve inversions, and so on. So what quantity is invariant does not change under a Mobius map. Okay? This is a geometric question. By the way, this question is very closely related to concept in art called perspective. That is, if you want to paint a picture of, let's say, railway tracks, right? Then you'll paint them like this. Okay, these are railway tracks. If you look at maybe if you want, if you look at a railway track from here, notice that these two lines, if you look at them in 2 dimensions, they look like they're about to meet, but in reality they don't meet, right? The 2 railway tracks are parallel. But if you want to draw a picture, then you have to draw it like this. This is called perspective. It's like taking a flat piece of canvas and looking at these railway tracks and projecting that onto this flat piece of canvas. And this study of perspective, that is, if from my perspective the railway tracks look like these, if you stand here and you look at these railway tracks and try to paint them, what will you paint? This is an interesting question, right? So the correct answer to this question, these questions are part of what is known as projective geometry. And this projective geometry is very closely related to Mobius maps. Okay. So what quantity is invariant under Mobius map? What does this question mean? Under translations and rotations, the distance between any 2 points on the plane is unchanged. What about for Mobius maps? Okay. Or in other words, what quantity is invariant under perspective? It turns out these two are the same question. Okay. Firstly, let us consider only very simple maps. f of z equals az plus b. What quantity is invariant under this? Such maps are compositions of translations, rotations, and scaling, right? If there were only translations and rotations, I could have answered this question very easily. The last transformation does not preserve distances, right? In fact, translations, all right. So, however, it does preserve ratios of distances, right? Scaling doesn't preserve distances between 2 points, but it does preserve the ratios, right? If you take these two, they scale, the ratios are preserved. So let us try checking if this particular complex number is invariant under this map, okay? So it is, that's homework, okay? So this particular complex number is in fact invariant under this map, right? I mean, the ratio you would expect it to be invariant, but in fact it's more than that, okay? The complex number is itself invariant, right? So Mobius maps take 4 distinct points to 4 other distinct points. So that take these 4 distinct points to these 4 distinct points, preserve this. What do I mean? We have only restricted our attention to these things, right? What are these kinds of Mobius maps? These are precisely the Mobius maps that fix infinity, right? They fix infinity, and they take Z1, Z2, Z3 to 3 other distinct points, W1, W2, and W3, right? So Mobius maps of this type preserve this number. What about any general collection of Mobius maps? What if a Mobius map takes these 4 points to these 4 points? What does it preserve? Okay. Now, this is not an easy question to answer. We can try trial and error. What can we try? We can try, this certainly won't work, right? So surely you have to bring Z4 into the picture somehow. So what we can try is that we can basically see infinity, so we should have something such that if you substitute Z4 as infinity, you should get this, right? So we can try multiplying this by something of the type Z4 minus something divided by Z4 minus something else. So we can try Z4 minus Z1 by Z4 minus Z2, or we can try something else. It won't work, unfortunately. So we can try Z2 minus Z4 divided by Z1 minus Z4. It's not a good idea to try Z3 minus Z4 by Z3 minus Z4 because that's stupid. That's just this, okay? So this works. Why does this work? Because I say it does, and because that'll be a part of your homework. Yeah, that's why it works, okay? This expression is given a name. It's called the cross ratio of these 4 points, okay? So the cross ratio of 4 points is invariant under Mobius maps. The cross ratio in general is invariant under perspective in the study of art, that is, okay? In projective geometry, that is. Okay? So since we are out of time, I'll stop here. Any questions?
Sir, what is the meaning of invariant?
Invariant means that suppose I take a Mobius transformation, then these 4 distinct points will go to 4 other distinct points under the Mobius transformation, right? I can calculate this quantity for these 4 points. I can calculate this quantity for those 4 points also. Namely, I can take W1 minus W3 times W2 minus W4 divided by W2 minus W3 times W1 minus W4. The miraculous thing is these two will be equal. That's what invariant means. That means this quantity is unchanged under Mobius maps. Is that clear?
Yes.
So cross ratio, what exactly it represent?
That is difficult. Honestly, even I don't know what it represents. Maybe you can try searching on the internet. And that is why I motivated it like this, the way I did. So if infinity is preserved, if you look at these special Mobius maps, then of course, this is the obvious thing to try, right? It doesn't preserve distances, but preserves ratios of distances. So you can try this and it is invariant. Here it's just by trial and error. I don't know if there's any geometric meaning. Maybe there is in terms of circles and straight lines, but I don't know, honestly. Any other questions?
I think Sudipta Mazumdar might have some question with regard to some stereographic projection.
Let me.
Yeah, he is there. Dr. Sudipta Mazumdar, do you have any question? I think he left, it seems.
Okay.
Okay, if there are no questions, let us thank Professor Vamsi for a very interesting talk. And we have given a very nice view of this conformal mappings.
You're welcome.